Okay, so here we are. Let's decide if the given series converges. If so, find the sum. So we won't always be able to find the sum, but I think we can here. If you were to write out several terms, what would they look like? So if you plug in 1, so this is your term for your nth term of your sequence, right? Or your formula, rather, for the nth term of your sequence. 1 over 2n minus 1 minus 1 over 2n plus 1. That's your formula for your nth term. And so you use it to find any particular term in your sequence. So what would the first term in your sequence be? Just to get a feel for what this is telling us. Plug in n equals 1 to get the first term. And by the way, it's not always n equals 1. It's whatever this lower number is that you plug in to get the first term. If it's 0, you plug in 0 to get the first term. So yeah, if you plug in 1 here, you get 1 minus, and then if you so you get 1 in that. It's always 1 in the numerator, and then you get 1 in that denominator, and then if you that'll get an odd number. 2 times 1 plus 1 is 3, so 1 minus 1/3. And that you kind of like think of that guy as your first term, even though we're not going to add them together. And then what would the next term be when you plug in 2 for n? What would the next term be?
1/3 minus 1/5.
Yeah, so you're plugging, you start with 2 here, and you get 4 minus 1 is 3, that 3 right there. And then minus, you plug in 2 here, you'll get 5, won't you, in the denominator? So 1/3 minus 1/5. I'm sensing a pattern. What's the next one?
1/5 plus 1/7.
Yeah, except it's minus.
Oh, minus 1/7.
And then we could do this all day long. So I just did that as an exercise to make sure you understand what that notation represents. But you can see something, right? You can see that some of these terms cancel, don't they? The minus 1/3, the plus 1/3, the minus 1/5, the plus 1/5. If we could figure out how to make use of that, maybe we could actually find the sum. But the thing is, it's really hard to do when you have a plus dot 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 on the end and it doesn't stop anywhere. So we go to partial sums. Okay. So in general, what does Sn represent? It's really the sum. I have to switch to I here for the what I would call the index. The sum from I equals 1 to n of a sub I, which denotes, A1 plus A2 plus A3 plus dot dot dot. It stops plus an. Now we're using n as the upper number that you plug in. So you guys see that, okay, here we're using n as our index. Here we're using n as our upper number. It's irritating, but most books do it that way, and you just have to get used to it. So if we make use of this sort of format, we'll have an end value here. And that could be useful. So let's rewrite these numbers, because the formula is going to be the same. But let's rewrite these numbers so that we have the nth term here. Okay, so what I mean by that is let's write down A1, A2, A3 just as we did before. We already know what those are. So Sn is going to be, okay, A1 is still this guy, isn't it? Because if you plug in, the only thing that changes in this formula when we write down the nth partial sum is we have to replace n with I. So it's 1 over 2i minus 1 minus 1 over 2i plus 1. It's just a notational thing. Let me do a better job, though, of writing that down. So in summation notation, it looks exactly the same as what you started with, except you replace n's with your new index. So 1 over 2i minus 1 minus a little bit of space here. 1 over 2i plus 1. There. Okay, so let's go ahead and write it out. We've already written it out. These first few terms won't change. The I doesn't, we call it a dummy variable because if you write it out longhand, it disappears, doesn't it? Yeah, so you plug in 1, you're going to get the same thing we had up there. You're going to have 1 minus 1/3 if you think of that as your first term. And then if you plug in 2, you'll have 1/3 minus 1/5. If you plug in 3, you'll have 1/5 minus 1/7. You know, let's go a little farther, though, so that we can really see the pattern. So that's what you get for the first 3 terms, if you think of a term in parentheses as one object. So, or the thing in parentheses is one term, that is. So then let's go, okay, so this was what we got when we plugged in I equals 3. What do we get when we plug in I equals 4? And you don't even need to look at the formula if you see the pattern, but let's look at the formula one more time. So if you plug in 4 there for I, what do you get? 1 over, well, 1/7, okay, and then minus 1/9. Everybody see that? Let's do one more just for fun. So if you plugged in, this would be the 5th guy, what would you get?
Plus 1/9 minus 1/11.
And I didn't even look at that. You can just see the pattern. I know, oh, the number here, this next number is just going to be plus 1/9. And then the next odd number up is 1/11, right? You subtract that off. Does everybody see the pattern? Okay. Now, let's put in the nth term. Let's put in a dot, dot, dot. Plus dot, dot, dot. And then what do you get if you plug in the nth term for I? Well, you get exactly how the formula was expressed originally, right? So you get 1 over 2n minus 1 plus 1 over 2n plus 1 as your nth term. Okay. Yeah, it helps to copy it down, right? Okay. Now we can grab a hold of this last term and get a formula without the plus dot, dot, dot if we see a pattern. And you do, but we need to cancel correctly here. So what's going to go away from left to right? We've got a minus 1/3, plus 1/3.
Everything except for the last term.
They make 0. Yeah. This guy, this guy, this guy, this guy. Okay.
That one, but not the next.
This guy. Well, no, in the plus dot, 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 there's going to be a 1/11th, right? Okay, so before we cancel one of these, we need to see the pattern. Okay, here's how you do it, you guys. Let's go with what your thought was. If this were the nth term, right? It's really the 1, 2, 3, 4, 5. So if we only were looking at S5, okay, what doesn't get knocked out? The 1/9 does, right? But the last guy doesn't. If we're only looking at the first 5 terms, S5, right? So that's the pattern. And you have to write down enough of them so you see it. I didn't need this many, but I wanted to make the point. Oh, now because of the plus dot, 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 there will be a 1/11th in the next term, right? So it will get knocked out. But now if it's the nth term,
So you knock out the first one
in,
minus 1.
and this guy doesn't get knocked out because we're not adding any more terms, right? Okay, that gives us an nth term formula without a plus dot, dot, dot. So let's write that down. The nth term formula is 1, this guy didn't get knocked out, minus 1 over 2n plus 1. Okay, why is that useful? Because if the series has a sum, a finite sum, it doesn't have to have a finite sum, but if it does, then it's equal to the limit as n goes to infinity of Sn. So the sum, the original series, I'm just copying down that original formula, sum n equals 1 to infinity of 1 over 2n minus 1, minus 1 over 2n plus 1. That is equal to the limit, if the limit exists, as n goes to infinity of Sn. But the limit as n goes to, this is by definition, this equality. But in this particular case, that's the limit as n goes to infinity of our formula for Sn, 1 minus 1 over 2n plus 1. And that's something we know how to take the limit of. So we put a series in terms of Sn, which is really a sequence of partial sums. And by doing that, we can now use the limit, our knowledge of limits, let's say, to figure out what that series converges to. What is this limit? It's just 1. We know that, and there's no work to show here when it's this simple. We know that this denominator is going to increase without bound. This numerator stays the same. So no work to show. We know this goes to 0, and we're left with 1. So this sum right here is equal to 1, believe it or not. Okay, is it really equal to 1? Can you really add an infinite number of terms? No, but it converges to 1. And if you add the first 1,000 terms, it might get really close to 1. Right? Now, this trick does not work every time. It's a very special kind of series that we're looking at. It's called a telescoping series. Can anybody guess why? Yeah, so it's like a pirate's telescope that you've seen in the movies, right? It expands out when you want to look at something, and then you collapse it down. That's exactly what happened when we did all that cancellation. So it's a good name for it. And so the telescoping, it'll be a telescoping series if it has the form, let me put a possibly in front of that. It will possibly be a telescoping series if it has this sort of form where you have a rational function minus another rational function. I suppose it doesn't have to be a rational function, but think of it as a fraction minus another fraction. It could be a telescoping series if it has that form. And so it's a classic trick for finding the sum.